next, I want to show you something that's a little bit peculiar with induction. And I'll give you a hint at where we're going. What I want to show you is that with induction, sometimes it can be easier to prove a harder result than a harder, more complex result than the simpler, sort of easier looking result. Okay. Okay, so next problem. Let's prove that n squared is less than or equal to 2 to the n for n greater or equal to 4. Okay. And this is to illustrate this concept that, a peculiar thing happens with induction, that sometimes something is easier to prove even though it's a stronger claim. Okay. So first thing, let's tinker. I want to show you why did we need n greater or equal to 4. Okay, so let's put n equals 1, 2, 3, 4, 5, 6. Okay, so let's tinker. Okay, and let's look at n squared, and let's look at 2 to the n. Okay, so n squared is 1, 4, 9, 16, 25, 36. 2 to the n is 2. Okay, so 2 to the n is bigger, but then 2 to the n becomes 4. Okay, so still bigger equal to, and then 2 to the n is only 8. Okay, so it's less than. Okay, so it's not always bigger equal to n squared. It's not bigger equal to n squared for n greater equal to 1. Okay, but now at 4, 2 to the n, is bigger equal to 16. It's actually equal to 16, so we get equality. So it's bigger equal to n squared. And then at 5, you get 32. At 6, you get 64. And now it turns out that it will always stay bigger. Are we sure it's going to always stay bigger? Are we sure n to the n will always stay bigger than n squared? Well, it turns out yes. And that's what we're going to prove with induction. So let's see how that works. Another inequality. Okay, so P of n is this claim. Okay, and we're claiming that this P of n holds for all n greater equal to 5. So let's for all n greater equal to 4. So this is going to illustrate a few new things. So proof by induction. Okay, so since we only need to prove it for n greater equal to 4, we only need our infinite chain to start at n equals to 4. Okay, so if we have an infinite chain of implications that starts at P of 4, and if we manage to prove this, then we've started the infinite cascade that's going to prove it. That's going to prove P of n for all n, on the right. Okay, i.e. for all n greater equal to 4, the infinite cascade of dominoes falling starts at n equals 4. So the first difference between this proof and all the proofs we've done so far is in the base case. Okay, so the base case. In this case, the base case starts at 4. So the base case is P of 4, which claims that 4 squared is less equal to 2 to the 4, and this is 16, and this is 16. So it's clearly true. Okay. And now let's continue. What do we continue with? The induction step. So it's always the same. This is the beauty of an induction proof. The proof mechanics is always the same. You have to prove a base case, you have to prove the induction step, and the induction step is always the same. You have to prove that P of n implies P of n plus 1 in a typical induction. Okay. And it may be tricky to prove, but the steps are always the same. So induction step. Okay. So what do we have to prove? We have to prove that P of n implies P of n plus 1. And again, a difference between this proof and all the proofs we've done before. We had to prove this implication for all n greater equal to 1. Now we don't. We only need to prove the implication P of 4 implies P of 5, P of 5 implies P of 6, and so on. So we only need to prove the implication for n greater equal to 4. So we have to prove this implication for all n greater equal to 4. Another difference, and that's related to the fact that the base case is only 4. We want to only show the claim for n greater equal to 4. Okay? So let's see how we'll go about doing this. Well, it's the usual story. In a proof of an implication, you can either use direct proof or contraposition, and the typical choice is direct proof. Okay? So we assume P of n. What is that? It's the claim that n squared is less equal to 2 to the n. And we want to prove P of n plus 1, which is the claim that n plus 1 squared is less equal to 2 to the n plus 1. Again, it's very important that you write down the claim P of n plus 1 because, you know, it's easy to make mistakes in actually translating the claim P of n to P of n plus 1. And I'm just going to mention that you have to replace every instance of n in the claim for P of n. You have to replace every one of those instances with n plus 1 everywhere. Okay. All right. So let us see. You know, we would like to make a claim about n plus 1 squared. So that's where we're going. So let's see what is n plus 1 squared. N plus 1 squared. Okay, now it's important. You cannot write down this claim as if it's true. But we're not going to write down that claim as if it's true. We're just analyzing n plus 1 squared. So everything we do has to be valid. And indeed, it is valid to say that n plus 1 squared is equal to n squared plus 2n plus 1. It's a valid step. Okay. Now, you observe that I have n squared here. Okay. Look, I got to assume that n squared is less equal to 2 to the n. So that means that this guy here is less equal to 2 to the n plus 2n plus 1. Okay. And it turns out that, you know, unless we can, you know, make some sort of non-trivial steps from this point, we're kind of stuck. Okay? Because we've certainly got, we're after this, but there's no easy way to see why this, you know, should be either equal to that or less equal to that. Okay? Now, this is where you need a little bit more creativity. You kind of build a wish list. Okay, you say, well, you know, what do I need to conclude that this is less equal to 2 to the n plus 1? And now we will observe that 2 to the n plus 1 is exactly equal to 2 times 2 to the n, which is exactly equal to 2 to the n plus 2 to the n. So I'm trying to prove that n plus 1 squared is less than or equal to 2 to the n plus 2 to the n. And here I've got n plus 1 squared is less equal to 2 to the n plus something else. And I would be done if this guy was less equal to 2 to the n. I would be done, because then I'd have 2 to the n plus 2 to the n, and I would be done. But, you know, I didn't get to assume that. I only got to assume that n squared is less equal to 2 to the n. Okay? So what do I do now? Kind of trapped. Okay. And now I'm going to show you this interesting phenomenon with induction, which says that sometimes when you're trapped and you build this wish list of what you would like to be true, sometimes you can add that to the original claim that you were trying to do. Okay, the original claim that you were trying to prove was that n squared is less equal to 2 to the n. What if I make the original claim harder or stronger? Okay. Suppose instead I made the claim, you know, let's call it now Q of n, which is the claim n squared is less equal to 2 to the n and, okay, 2n plus 1 less equal to 2 to the n. So that would certainly, you know, solve my difficulties here. Okay. And let's compare this claim Q of n with this claim P of n. Well, you know, P of n is the claim n squared is less equal to 2 to the n. Q of n is the claim n squared is less equal to 2 to the n and something else. So I have to prove two things here. Okay. And now here's the peculiarity. I'm going to go and prove those two things. Okay. And it's going to be easy to prove those two things. But it's much harder. Well, not much harder, but it's harder to prove the original claim. And you say, whoa. How is that possible? How is it possible that it's going to be easier to prove this quote-unquote stronger claim when we already had difficulty proving the easier claim? So, you know, that's the peculiarity with induction, and, you know, the high-level reason for why it can be harder to prove, why it can be easier to prove a harder claim is, you know, the main sort of difficult step in an induction is usually the induction step, where you have to prove an implication. So it's true. You have to prove something harder. Okay? But you get to assume what's on the left-hand side here. Okay? So you get to assume more. So you get to assume more, and you have to prove more. Okay? If you're trying to prove something harder. Okay? And sometimes the little bit extra that you get to assume is enough to allow you to prove that little bit more. Okay? And we're going to see that in action here. So, it's a little bit scary. I couldn't prove this guy, okay, but I'm going to prove more here. And why do I say this is stronger? Because if Q of n is true, then certainly P of n is true. Certainly. Okay? Because, Q of n involves P of n and something else. So if this is true, then this and that are true. So this is certainly true. Okay, so let's prove this harder claim by induction. Proof. Okay, proof. So, by induction. So, the base case. Again, we're interested in n greater equal to 4, so we need to prove Q of 4. Okay, well, what's that? That's the claim that, 4 squared is less equal to 2 to the 4, which we know is true. And, okay, 2 times 4 plus 1, so 2 times 4 plus 1 is less equal to 2 to the 4. So this is 16, and this is 9, and so that's also true. So we've proved the base case. Interesting. Okay. So, the conclusion is that Q of 4 is true. Now the induction step. Okay. It's the same induction step. The only difference, the only thing that's changed is I have a new claim, which is a stronger claim. It's just Q. So we're proving Q, not P. So the induction step is I have to prove Q of n implies Q of n plus 1 for all n greater equal to 4. So I get to assume, what do I get to assume? I get to assume Q of n. So I get to assume that n squared is less equal to 2 to the n, and 2n plus 1 is less equal to 2 to the n. Now I need to prove Q of n plus 1. And this is where I said that, you need to be careful when you write down what is the claim Q of n plus 1. So you need to substitute n plus 1 for n in every instance of n here. So this is the claim, n plus 1 squared is less equal to 2 to the n, and, 2 to the n plus 1, and now I have to replace this n here by n plus 1. So I get 2 times n plus 1, okay, which is 2n plus 2. So and then 2n plus 2 plus 1 is 2n plus 3. So I have to prove that, n plus 1 squared is less equal to 2 to the n plus 1, and 2n plus 3 is less equal to 2 to the n plus 1. That's what I have to prove for the induction with Q of n. Okay, so let's go ahead and do it. So I need to prove this. So I need to prove that n plus 1 squared less equal to 2 to the n plus 1. n plus 1 squared is equal to n squared plus 2n plus 1. But that's no problem, because n squared is less equal to 2 to the n, and 2n plus 1 is less equal to 2 to the n. And I got to assume that because I can make those claims because I assumed this and. So this is true and that is true. So this is less equal to 2 to the n, and that is less equal to 2 to the n. So this is less equal to, so here we have less equal to 2 to the n, and here we have less equal to 2 to the n. So the whole thing is less equal to 2 to the n plus 2 to the n, which is 2 times 2 to the n, which is 2 to the n plus 1. So I have proved this. So you see, even though I'm technically trying to prove something harder, this at least this part of the induction step was much easier than trying to prove it here somehow. Okay, because I got to assume more. I got to assume both this guy and that guy. That's what made this proof go through. I got to assume more in the proof. Okay, am I done? No, because I have to prove Q of n plus 1, which is an and. Okay, here I only had to prove P of n plus 1. Here I have to prove Q of n plus 1. And that is the price you pay in the induction for getting to assume more. You also have to prove more. So I not only have to prove this guy, I have to prove that guy as well. So I have to prove that 2n plus 3 is less than or equal to something. But 2n plus 3 is equal to 2n plus 1 plus 2. Okay. And look, 2n plus 1. I from my assumption, from my induction hypothesis, I have that 2n plus 1 is less equal to 2 to the n. So this is less equal to 2 to the n. Well, and this is 2, which is certainly less equal to 2 to the n when n is bigger than or equal to 4. So this is certainly less than or equal to 2 to the n. So this is less equal to 2 to the n plus 2 to the n, which is 2 to the n plus 1, as required. So I proved that. So I have proved Qn plus 1. Proved Qn plus 1. So therefore, Q of n plus 1 is true. And that's the induction step. I proved that Qn implies Qn plus 1. And so therefore, by induction, I'm done. By induction, Q of n is true for all n greater or equal to 4. Okay. And why 4? Because I only proved this implication for n greater or equal to 4, and my base case was 4, was n equals to 4. Okay, so let me summarize. This is kind of stunning. Okay. I tried to prove something, and somewhere along the way, in the induction step, I got stuck. I make a wish list. You know, it would have been nice if I got to assume that this is less than or equal to 2 to the n. And that wish list, I have to add to the claim. Okay, so then I came up with a claim that was stronger, a stronger claim. But somehow, miraculously, and this is the peculiarity with induction, somehow this stronger claim became easier to prove. Okay. And let's see exactly how that happened. Okay, how did that happen? Well, in this stronger claim, what I got to assume was two things. I got to assume this stronger claim for n. Okay, I got to assume, n squared is less equal to 2 to the n, and I got to assume this part. Okay. And being able to assume that part allowed essentially this step to go through. Okay. It allowed me to conclude that n plus 1 squared is less equal to 2 to the n plus 1 effortlessly. Okay. So, as expected, that wish list, adding this into the induction claim, into the induction hypothesis, helped me to get this step through without any effort. But then there was a price to pay. That's not all I have to prove. Okay. I have to prove the added step. That's the price I have to pay. This added part that I added to the claim, I have to prove that as well. Okay. So I had to prove that, but that turned out to be not so hard. Okay. So in an induction, when you're trying to prove an implication, and that's the beauty of implications, it can be easier to prove a harder implication in the induction step. And that's because when proving an implication, you get to assume this, you have to prove this. Okay. And it is true that the claim is harder. So that means that what you have to prove is more, but you also get to assume more. And if you balance that just right, if you balance what you get to assume with what you have to prove, that's when the induction works effortlessly. Okay? So there. Summary. Sometimes with induction, and this can also happen in other kinds of problems and other kinds of proofs that you'd like to do. But sometimes with induction, it is easier to prove something that's stronger because of this balancing act that goes on between what you get to assume and what you have to prove in the induction step. The base case will always be harder because in the base case we had to prove more as well. But when you're proving the base case, you don't get to assume anything. It's the induction step that gets hard, that gets easier, that can get easier when you have a harder claim to prove, a stronger claim to prove. And that is something that's somewhat unusual with respect to induction. Okay, so let's erase. And let's get back and do more examples. By the way, so this is the original claim and it follows from Q of n. And here is the strengthened claim. Sometimes we refer to that as strengthening the induction hypothesis. Because in the induction hypothesis, we got to assume more. So we strengthened that. We gave ourselves a base from which to move that's stronger. And it allowed us to prove that stronger thing for n plus 1. So this is sometimes called strengthening the induction hypothesis. Speed erase. Yeah. Boom. Okay, so let's do another example, and just to show you that, induction is very powerful. We can use it to prove all kinds of things, not just formulas. Okay. And, so we're going to go into L-tile land. L-tile land. Okay, so what's an L-tile? So think of like a Tetris tile, but not a Tetris tile. So, that's an L tile. Three grid squares in the shape of an L. Okay, and think that you can rotate, flip, whatever you want. Okay, so you can rotate this thing around, and the goal is we're going to look at some grids, okay, and we're going to ask whether they can be tiled using L tiles. Okay, so let's start small. So in other words, let's tinker a little bit, and let's look at the 2x2 grid. So this is the 2x2 grid. So this is 2x2. Okay, and imagine that on one of these squares, I'm going to remove one of these squares. Let's say I want to grow a tree there, and the rest of this patio I want to tile. So I'm going to remove a center square. There's no real center square, so I'm going to remove this square. Okay, and I can grow a tree there, and I need to tile this, and no problem. Okay, I can just place a tile here, and that's an L tile I rotated. I rotate it this way, and I can place it here. So I can tile the 2x2 grid after removing one square. Okay. Let's look at the 4x4 grid. So similar situation. Let me just draw the 4x4 grid. Okay. Okay. And again, I'm going to remove one of the center squares. Again, there are 4 center squares, but I'll remove one of them. Okay. So let me remove one of these. And now is the interesting question. Is it possible to tile what remains, the patio that remains, with L tiles? And yes, and let's see how we can do it. Okay, so what I'll do is I'll place one tile here. Okay, look at how beautifully I can color tiles. Feel a little bit like Bob Ross here. Okay, now what do? Well, I have to tile the rest, so let me place a green L here. I'm just using different colors. It's not that the tiles have different colors. I'm just using different colors so that you can see. Okay, so I'll place a green one here. Okay, no problem. Okay, and I'll place a red one here. Again, no problem. Okay, I'll place another red one here. And you can see that I'm going to be able to complete the tiling. Okay, with one more tile here. Let me make it green. Look at this beautiful picture. Wow. Okay, now make this green. Okay. So this is the 4x4 grid. And we can ask, can we do this for the 8x8 grid? So you see the idea here. This is 2 to the 1 by 2 to the 1. This is 2 to the 2 by 2 to the 2. So the next, the next grid in this progression. And there are other grids we could ask, can we tile? But for the moment, I'm looking at powers of 2. Okay. So let me draw the 8x8 grid. Okay. And 8 by 8 grid. Look at this. You can draw with me. Look at how beautifully I draw grids. Okay, so there's the 8 by 8 grid, and I'm going to take one of these center squares and, remove them. Just one. Okay. So, they started out with 64 squares. I removed one, so that's 63. And the L tile has 3 squares, and it's a good thing that 63 is divisible by 3. So this is the 2 to the 3 by 2 to the 3 grid. Okay, so 8 by 8. Okay, now, can we tile this? Okay, now I'm going to show you the idea. Okay, but you can go ahead and complete the tiling. I claim yes, and the way I'm gonna start this tiling is I'm gonna observe that this 8 by 8 grid is actually 4 by 4 grids. So I'm gonna draw a line here and a line here. Okay, so I've decomposed this 8 by 8 grid into 4 by 4 grids. And I observed that this center square will be in one of these 4 by 4 grids. And so what I'm going to do is I'm going to place an L tile. Okay, I'm going to place one L tile to cover the 3 squares that are in the other 4 by 4 grids. Okay, so I'll place one tile in here so that it covers a square in each of the 4 by 4 grids. Okay. And now you see that I've got 4 similar looking 4 by 4 grids, and if I can tile, each of them, then I will accomplish a tiling of the entire 8 by 8 grid minus 1. Okay. And that's the idea behind how I'm going to solve the problem for 8 by 8. And this, so if I can solve the problem for this 4 by 4, then I can solve the problem for the 8 by 8. And that's the essence of induction. That if you can solve the problem if you can solve your task for a smaller instance of the problem, then you can show that you can solve it for the larger instance. That's the basic idea behind the sort of induction step. The P of n implies P of n plus 1. Okay, so here's P of n, and that implies P of n plus 1. Think of this as smaller problem. Yeah, and if you can show that this is true, then think of this as the larger problem. So if it's true for the smaller problem, then it's true for the larger problem. That's sort of like saying, if I can solve it for the smaller problem, I can solve it for the larger problem. Okay? And that's the basic idea behind induction. Okay? And so I claim that no matter what n is, the 2 to the n by 2 to the n grid minus a center square can be tiled with L tiles. So claim the P of n, the 2 to the n by 2 to the n grid minus a center square can be L tiled. Okay, now why do I say a center square? Because actually there are 4 center squares in any such grid. Okay, and so you can pull out any one of those center squares and you can tile it. Okay, so let's prove this by induction. Proof by induction. Okay. And, it's going to now once we decide to prove it by induction. So let me emphasize, a proof by induction may or may not work. Okay. But once we decide to prove it by induction, the mechanics is very straightforward. It's always the same. So first step, base case. Step 1, base case. So when n equals 1, so P of 1, the 2 to the 1 by 2 to the 1 grid minus a center square can be L tiled. So we just showed this here. Actually, there are 4 different center squares you could remove, and each of them can be L tiled. So the base case we verified. Okay, is P of 1 is true. We verified it. Okay, This is the basic idea behind induction. The mechanics is always the same. Induction step. I induct step. So now we need to prove P of n implies P of n plus 1. Okay. And, so we have to prove this implication. So we assume, we're going to use a direct proof. So assume P of n, this is the very standard induction template with a direct proof of the implication. Assume P of n, what does that assume? It assumes that the 2 to the n by 2 to the n grid minus a center square is L-tilable. Okay. And now we have to show or prove P of n plus 1. So this is the induction mechanics. So to prove P of n plus 1, what is P of n plus 1? So it states that the 2 to the n plus 1 by 2 to the n plus 1 grid, minus a center square is L-tilable. Okay? And so how do we prove this? Well, we're going to use this basic idea that I illustrated, and hopefully you'll go and now tile the remaining 4x4 squares in a similar way to how we tiled this. Okay, slightly different. Okay, but we're going to use this basic idea that when you move from n to n plus 1, so 2 to the n goes to 2 to the n plus 1, it multiplies each dimension by 2. So it basically, if you have the 2 to the n by 2 to the n square, so here's the 2 to the n by 2 to the n square, 2 to the n by 2 to the n, then 2 to the n plus 1 by 2 to the n plus 1 simply adds another square here on each dimension because it's doubling. Okay, so now this is 2 to the n, this is 2 to the n, and so this together is 2 to the n plus 1. This together is 2 to the n plus 1. Okay, so that's what the 2 to the n plus 1 by 2 to the n plus 1 square looks like. It's composed of 4 2 to the n by 2 to the n squares. Okay, and now we're removing the center square. So this guy is removed. Okay, and we ask whether we can L-tile this. Okay, so I'm going to use this idea. Okay, I'm going to place one L-tile here. Okay, so I'll place one L-tile here. Okay. And now it would be great if I could somehow use the induction hypothesis, which I was able to assume, to L-tile each of these these 2 to the n by 2 to the n squares independently. Okay. And the problem is I cannot. Okay. The problem is so it is indeed the case that this is a 2 to the n by 2 to the n square that's missing. So it's a 2 to the n by 2 to the n grid that's missing a square. So this is a 2 to the n by 2 to the n grid that is missing a square. Okay. But P of n does not allow me to conclude that I can L-tile it. But P of n does not allow me to conclude I can L-tile. And the interesting question is why? Okay, why? Okay. So now this is important. Okay. So the whole idea in an induction is to somehow be able to use your assumption to help you to prove the higher case, the P of n plus 1 case. Okay. So we have to look very carefully at our induction hypothesis, our assumption. Okay. And what does the assumption say? The assumption says very clearly that the 2 to the n by 2 to the n grid minus a center square can be L-tiled. The problem here is that this 2 to the n by 2 to the n grid is missing a square, but it's not a center square, it's a corner square. And that's the same with all of these guys. They're all missing not center squares, they're all missing corner squares. So, we cannot use the p to the n assumption to tile that. Because it's not this grid, this smaller grid is not of the form to which we can apply p to the n, p of n. Okay, but now let's remember back to the other problem where we were trying to prove something and then we got to a point and the induction hypothesis alone wasn't enough to allow us to conclude that p of n plus 1 was true. So we said, well, let's build a wish list. What else would we like to be true? So we would like not only that you can L-tile the grid if it's missing a center square, but we would also like that you can tile the grid if it's missing a corner square. So let's prove the stronger claim that I can L-tile a 2 to the n by 2 to the n grid if it's missing a center square or a corner square. That's stronger because it's two things. Okay, but that's what I need to make this go through, and hopefully by proving this stronger claim, I can balance what I get to assume with what I need to prove and prove everything. Okay, and indeed that's the case. And let's now go through the proof of this stronger claim. So this is another example where, this peculiar thing with induction occurs where, I'm trying to prove something I cannot. Okay? And I see something else that I need, kind of like a wish list. Okay? So let's add it into the claim. Let's make the claim stronger by adding my wish list into the claim. Okay? So stronger claim. Okay. The 2 to the n by 2 to the n grid minus a center square can be L-tiled, and the 2 to the n by 2 to the n grid minus a corner square can be L-tiled. You see, I'm adding something more to prove. Not just that if it's missing a center square, it can be L-tiled, but also if it's missing a corner square, it can be L-tiled. Okay, so instead of calling this P of n, let's call it Q of n. A new predicate, just not to confuse it with the original one. I want to emphasize it's a stronger claim because it's an and. I have to prove two things. And if Q of n is true, then that immediately tells you that P of n is true, because this is including, the center square case as, one of its claims. Okay? And it turns out that this we can prove with induction. Okay? So let's go through that proof now very quickly. Okay, so the proof is exactly the same. The mechanics is exactly the same, and I'm going to emphasize that by just leaving the sort of infrastructure, the scaffolding of the proof intact. I'm just going to erase the P of n part, and we're going to replace that with Q of n. So this stuff, so the mechanics of the induction proof stay the same. Okay? And let me erase this picture, and we'll put a new picture on. Okay? So, induction step. So the proof by induction of Q of n. So we need the base case, which is Q of 1. Q of 1. Okay. The 2 to the 1 by 2 to the 1 grid. 2 to the 1 by 2 to the 1 grid. Missing center or corner square is L-tileable. Well, the 2 by 2 grid, the center and corner squares are all the same. If you take out the center square, that's the same as a corner square, there's no difference. Okay? And if you feel like tinkering a little more, go and see if in the 4 by 4 grid, if I remove a corner square, can I L-tile? And you can see that it'll clearly be the case, because if I remove this square, all I do is place this red L-tile over here. Okay, and I've got this box, and then everything else stays the same. Okay, so the 4 by 4 can be done. Okay, so we've verified more than just the base case, but that's okay. It's perfectly fine to tinker a little more than you need to. What's not fine is to tinker less than you need to. Okay, now induction step. assume Q of n. Okay, what does that mean? The 2 to the n by 2 to the n grid missing a center or corner square is L-tileable. Okay, so that's what we get to assume, that if you have the 2 to the n by 2 to the n grid, and if it's missing a center or a corner square, we can L-tile it. Now we need to prove Q of n plus 1. That is the 2 to the n plus 1 by 2 to the n plus 1 grid, missing the center or corner square is L-tileable. Okay? So, important. We get to assume more, but we also have to prove two things. And that might look hard. Okay? But it turns out in this case, the induction hypothesis is enough to prove these two things. So it's a case of you need to balance when making a claim, the strength of the claim should be such that what you get to assume balances what you get to prove. Okay, so you get to assume enough to prove what you need. Okay. All right, let's prove it. Well, there are two things to prove. So let's consider the bigger grid, which is twice as big. Okay. So here we have 2 to the n, 2 to the n, 2 to the n, 2 to the n, and it's missing a center square. Okay, no problem. And it could be missing any center square. The argument is basically the same because all the center squares being removed are equivalent because you can just rotate the grid. Okay, and the second case we need to prove is that what if you've taken out a corner square? Okay, so you've taken out a corner square. Okay, so again, this is the 2 to the n plus 1 grid, so it's 2 to the n, 2 to the n, 2 to the n, 2 to the n. So that gives you the 2 to the n plus 1 grid. But now you've not taken out a center square. We need to prove two things now because we've got a stronger claim. Here we've taken out a corner square. Okay, so what I need to show is that both of these can be L-tiled. Okay? And okay, you might say, well, what about if I take out that corner square? Just rotate it and it becomes this corner square. It's that corner square, just rotate it and it becomes the top left corner square. So sometimes people say, without loss of generality, assume that the corner square that's removed is at the top left. And we can say, without loss of generality, assume that the center square that has been removed is in the top left quadrant. Okay? So here's the basic idea. Place an L-tile here. Okay, so that it occupies the three 2 to the n by 2 to the n grids that do not have a missing square. Okay. Now, I have 4 2 to the n by 2 to the n grids, and each of them is missing a corner square. But I know that that can be L-tiled by the induction hypothesis, because the induction hypothesis says 2 to the n by 2 to the n missing a corner square is L-tileable. No problem. So, this can be L-tiled on its own. This can be L-tiled on its own. This can be L-tiled on its own, and this can be L-tiled on its own. So that means the whole thing can be L-tiled by just, using the independent L-tilings of each subgrid. What about this guy? Same idea. Okay, place an L-tile right here, occupying the three grids that have not got a square missing. Okay, that effectively removes one square from each grid. So now each of these grids, okay, so this grid is a 2 to the n by 2 to the n grid missing a corner square. And this grid is a 2 to the n by 2 to the n grid missing a corner square, so they're all missing a corner square. So this grid can be independently tiled because we got to assume it. We got to assume that if you're missing a corner square, it's L-tileable. This is L-tileable. 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 So that means that the 2 to the n plus 1 by 2 to the n plus 1 grid, if it's missing a center square or if it's missing a corner square, in either case, you can L-tile. And that proves Q of n plus 1. So Q of n plus 1 is true. It's the end of the induction. Therefore, by induction, Q of n is true for all n greater or equal to 1. That's the end of the proof. By the way, for this particular example, you might think that this is a much stronger claim than what we originally had, because we originally wanted to prove it for center squares, but now we proved it for center squares and corner squares. It turns out that we can prove a much stronger claim, and it's just as easy to prove by induction. So let me call this R of n. Okay, and you can now sit down and try to prove this. And that's just an exercise. A 2 to the n by 2 to the n grid missing any square is L-tileable. L-tileable. Okay, that is hyper strength. Okay, what could be stronger as a claim than that? You can take out not just a center square, not just a corner square, you can take out any square you want, and it can be L-tiled. Any square you want. Wow. Prove it by induction. Okay. Meanwhile, let's do the speed erase and keep going with examples. Induction by osmosis.